Hi, it's KOJRO again. It's been a week since my last video, and my last video was about EPROMs. I was using this contraption to measure delays in EPROMs, but I just made that video and I started to think, why did I even do this? The problem I wanted to dig into sort of was what kind of EPROMs can I expect to use on the 5170, and I did test with a 250 nanosecond EPROM. In fact, I tested with a lot of them because I tested all the non-BIOSes, 4 of them, and I also tested with an XT-IDE BIOS in the same settings, and all of them are 250 nanosecond chips. Or I do think two of them was 200s, sorry, but most of them was 250 nanoseconds, and they worked just fine. So I know that this is able to work with 8 MHz CPU and the 250 nanosecond chips, even though the specification is 119 nanoseconds. So I'm not sure that this works in every setting, but at least I know that it did work with my test setup here. That is really simple. It's just IDE interface and a VGA card and a simple SD card, not SD card, a compact flash card to IDE adapter, a passive one, not any active ingredients in that one. And I have a lot of thoughts about making more videos for the 5170, and I need to prioritize my time with videos in the coming months, because I have a lot of things I really want to dig into. So I'm going to do some short things now with the 5170, and the first thing I'm going to do is actually measure out what I should have done to begin with. In the last video I'm just going to measure the timings with the EPROMs on my real life 5170 and see what's happening. What is the delay? What happens when the output enable goes low and you have address on the address bus? How long before you get something on the data bus? It's a really simple measurement. But to measure this good enough, I've picked out 3 scope leads, and I'm using my Rigel scope up there to do that. And I have a simple capturing software running on this computer behind me. And you can also see the 5170 is booted into the DOS screen on this LCD behind me. So this is my whole setup, and I'm just going to present what I did for measurements, and I'm going to present you for the results. So, to the bench. Yeah, now I'm back here at the bench and doing what I should have been doing all along. It's really stupid of not doing this first before I set into making this contraption here on the breadboard, because if I was worrying about the timings on this motherboard and the chip delays, of course I can measure this on in circuit here, but I can't of course change the chips out willy-nilly and test. I can of course test with different chips that is burned into this ROM, but with the 256 chips that is required here, I didn't have the same range of chips available to test. So the last video I did get some captures with my El Cheapo scope here, and it's really good to these basic measurements, but for this I had to dig out my Rigol DS1054 scope. And what should I say? The answer did not surprise me, but there is some I can tell you what I'm measuring here. This scope lid is connected to the A0 line. This is connected to the D1 line, and this is connected to the chip enable. I can of course bring out a fourth scope probe and measure on the output enable also and measure that delay, but that is really not important for what we see here. And walkthrough of what I did measure. I don't have a good way of capturing the screen on the Regal scope live, so I can connect this to my PC and grab the screenshots, but that will be static screenshots. I am looking for a way to actually be able to either film or look through the Regal scope direct, but I do suffer a bit from lack of equipment to do that. But I'm using this rather simple Regal screen capture software that is available online, and I found this of the EEV blog. You know, the guy that used to talk about electronics and stuff, but now have, almost quit doing that. I loved watching his tutorials back in the day when he was really doing electronic blogs and stuff, but not so much now. And I will go through the details more on the computer, so I will show you that then. And I might do some more measurements here afterwards. But until then, I just turn this off again. And by the way, I'm loading this now with the device that we set up last time. It's a bit difficult to grab this out here, but it's the 120 megabyte SD card with the DOS boot, and the computer is now standing booted into DOS with the mode select code page function completed as the last line. So it's just as we saw in the video where I did test the BIOSes on this motherboard. And some of you also asked me to test if there is a speed difference with reading the drive if I'm using the BIOS for the XT-IDE or if I'm using this Quadtel BIOS, and I'm probably going to check that as well. I will see what the time allows for in this video. First, I think we are going to look into how the EPROM chips or ROM chips actually are wired. And here you can see this is both sets of EPROMs and odd and even chips. They are a pair. The U27 and U47 are the BIOS-ROMs, and the U17 and U37 are the option ROMs. And there ain't much difference to this, and it's a bit hard to see even, but it seems like how they have drawn this whole section here, I can just take this away, that they have paralleled these chips. And you have some noticeable stuff here. You can see here that pin 1 is marked not connected, but it's fixed to the plus 5 volt supply here, and that is to use EPROM, because if you don't tie the pin 1 too high, then the EPROM won't be enabled. So this is one of the operation conditions for an EPROM. I don't think that's necessary for PROMs. And you can also see the signals we are measuring on here. This is the memory read signal, and it goes on to the chip select on all chips. And that means that all these chips are selected and are going to draw power simultaneously, and that is meant when you are doing a memory read. So it makes sense, you couple in the ROMs when you do a memory read. And the output enable is toggled by U17, so the U17 and U27 is never allowed to operate at the same time. So that's the output enabled, it's coupled to each on an output on a flip-flop. You also have this A14 line that they have made something special with. It goes to a jumper block up here, and I'm not sure why they have done this, because normally when you do this it's because you're going to change the address space or the size of a EPROM like they have done it, because this is the highest address bit. So I'm not sure why they done this, but it can be to allow for smaller EPROMs and I have seen that people has used 128 EPROMs in these, but I have not tried that. And it also can be to change the address space, but again, I have not dived into this. So the other lines we are measuring is the A0 line for making sure that we have an address, and we are using this to make sure that the chip is enabled. We use this as a trigger, and we are measuring the output on the D0 line. We could have used any one of the data lines, but we have chosen to use measurements on the D0 line. There should be no difference in the timing outputs on any of the data outs here. So it's the same method of measurements that we did in our last video when we did this on the breadboard. And what are we measuring? This is just a sketch, and this is one of the drawings, and I'm just going to, we are going to go into more detail on this, but just to make this clear, we are making, I can change the color, we are measuring chip enable, address 0, and D0. We are triggering on the chip enable signal, and we see how the timing fares on this one. And here you can see we do have a stable address line, and what we see here is a transition on the D0 line with a timestamp that is a delay from here to here, a delay like that, and that is what we are measuring. And you can see here the scope has a time base set to 50 nanoseconds. So one of these lines from here, not lines but squares from here to here, is 50 nanoseconds. So that is what we are measuring. And the biggest delay on any EPROM, and what is noted in the datasheet and what is also given in the manual for the 5170, is this delay here from chip enable to a stable output on D0. And mark here that even though I see here that I have a data out, I'm not sure that this means that this is stable. In some cases we might get a signal that is out here, and that might be why IBM has marked that this should be 190 nanoseconds. So that means we are over here somewhere with this delay. So we do have a margin here from 130 nanoseconds, that is what we measured, and up to here it's about 1 square. Sorry, I marked this wrong, it should be here, but you get the gift of this. It's 190 nanoseconds, that is the maximum timing that IBM allows. And here you can see this timing from the datasheet. This is the one we are measuring. Valid output, that means we have a stable data output from the time we put chip enable low, and low and is when it passes 0.8 volts going down on this edge. So we are going to check this out, and I've done several measurements on this, and this is our result. This is measured on U47 and this is measured on U27. And that is to make sure that we don't have a huge variation of timings and other stuff amongst two EPROMs. That should be about identical. And you can see here that we do have some situations from here. This is a bit undefined, but the high is measured on this datasheet we have here, is measured to about 2 volt. And that is differing a bit from the datasheet we used last, that was 2.4 volt. But we can be a bit liberal about that because it doesn't matter much. And you can see here we do have a stable address bus, and we do have this transaction here that have a delay. Here you can see this is the flank, and this is stable data, so you do have a timing delay from here to here. And same here, you do have a stable address line and you have a delay here. And you can see the same over here when we are measuring on the U27. But on the U27 we do have some shorter delays sometimes and some longer ones, so it's not as stable the measurements on U27 as they was on U47. That might be to production spread, that might be to measurement glitches, I'm not sure. But that is what we are measuring. And to point this out, about 1 volt or something I measured from here, and about 2.4 volt to make this consistent with what we had last time. And then we are measuring from the time this reaches downwards to 1 volt, and then I'm measuring here to this is reaching about 2.4 volt upwards. And the timing is what we have here, and this is 50 nanosecond. And if I draw this so it's actually meeting the line here, you can see that it's hitting somewhere here. So we have translated that to about 130 nanoseconds, and that is about the average we have on these. So the delay we are actually measuring is 130 nanoseconds, and this is on a 250 nanosecond chip, or two 250 nanosecond chips. So that's why this is working. The chips are working much faster, have a shorter delay than actually stated in the datasheet. And why is this? I'm not sure, but one hypothesis or statement I can make about that is they was making these chips in 250, 300, 180, 120 and hundreds. And did they even make all these variations, or did they just have a test rig to see how good they performed and sort them into different bins? I'm not sure, but that's one theory, and that meant they have to fulfill some orders for 250. They got less paid for them than the 180s, but they was ramping up productions, they had a good run, so every one of the chips was performing like we say here, 130, 150 nanoseconds. But to be able to sell the chips a bit cheaper and differentiate, they sold the chips with different markings, but every one of them was performing better than what actually was stated on the ceramics of the chips. That's just one theory, but it does seem to be the most likely explanation. So now we are going to measure something else. What we are going to measure out here is something that I got as a suggestion from a viewer. I've turned this off now, so I'm going to disconnect these measurement leads, the scope probes. I just put them over here, and what I used for testing this is actually this clip that clips over the IC and gives you a way of hanging on measurement hooks and stuff. So very good device, but of course it does introduce some it's a way to introduce some noise into the system. But now we have put our BIOS is the Quadtel. We have removed the XT-IDE Bios, and I've loaded this with the Cisco 32 megabyte card. It's the oldest card. If it's the slowest, I don't know, but we are going to try to test and measure some drive parameters and such. And I'm not testing this with a spinning disk, I'm testing this now with the compact flash card, and that might introduce some problems. So we finished booting. I do have check disk on this. What did I name it? Like so, and check it, and it actually did hang. That was interesting. I wonder if there is something instabilities in my system. Have I done any changes on this? I actually done just measurements. The EPROMs are okay. The speaker should make no contact on anything. The battery is connected. Power is connected. VGA. I can actually, for the time being, I can just leave out this diagnostic card and just keep the IO card. And we try again. System is booting, and normal HiMemsys error messages. Check it is running. And benchmark, I can do the main system benchmark so we see where we're at. And it's an 8.01 MHz 286. That comes as no surprise. And you are testing this. So this looks pretty normal. And you have some hard drive test here. And I do seem to remember that this is not a very good way of testing, but we do have 1280 and it's working with the average and track seek times. I do think those will be very low with this testing regime. Aborted seek error, so it didn't measure that at all, but it's 15.07 times faster than an IBM XT with this SD card. And I'm also going to check this with another tool. I had this I think it was this is the James Purse disk test, and they are doing actual writes and reads and tell us what to do. 777 1163. The next thing I'm going to test is to test 128 compact flash card again to see if this performs better. It should perform better. I can't remember every result, but I do think we will get the gist of it when we test this. And afterwards I'm going to install the original BIOS, and I'm going to install the original BIOS. Do I dare that? I don't have the configuration utility, so I will just add the XT-IDE Bios onto this. Yeah, 14.4 sector random read and 13 on this. And I'm going to test now with the other card. So, and I have to enter the BIOS to alter the drive parameter settings. Yeah, that's the setup. And the other drive has the 980 and 32 sectors. And yeah, just put this, it doesn't matter, like so, and F10 save, and we try to boot. Yes, and we do the check it first. And benchmark, hard drive. Yeah, 1300 and something, and the other one was 1200 something, so this is definitely faster. And it was also able to determine the average track and seek times, and it's 0.4 milliseconds. I do seem to remember that a normal hard drive in this here was from 30 to 200 and something milliseconds, so I'm not sure, I might remember that wrong. And 15.67 times IBM XT, and it was 15.0 something on the other. So this card is a bit faster. And we will also check the other utility. It's the disk test. And this is the James Pierce test, and we do see here that it's 678.1163. I do think this is faster, but I can't remember the exact figures. But I do seem to, it looks like the test is actually performing faster to get to the end. 11.5 IO flops, IO operations, sorry. Yeah, 14.4, so this card I do think is faster. But then I'm just going to make this powerless, and I'm going to add the XT-IDE Bios chips from our test. And first have to check that the legs are okay. We did have a problem with that last time. And this is the 17, it's the one that's going in this socket here. Like so. And the 37. I do think that went okay. And I have to go into the BIOS here and enter the no disk alternative. Setup. And here I like so, and F10 and escape. And now it should boot with the XT-IDE BIOS. Yeah, and it did find the drive. It's 128 compact flash, and it's starting. And the difference between this 1278, 1272 and 0.5, 0.5. We had 0.4, 0.4, and I do think we had a little bit faster speed, but we will be able to compare this in a moment. So I do think that this actually is a bit slower, and let's see on the other tool. It was test disk test. Oh, 66602. That's definitely slower than it was. I wouldn't think that this would make so much difference, because it's just the interrupt 13 routines and the interrupt 21, I also think, that is actually doing anything. And of course we are running this now. It should be the same with the access to the code, and the other stuff. And these chips is exactly the same, so the read-write speed from the ROM, the read speed from the ROM should make no difference. And 11.6 and 13.7, so it's definitely slower. I can test once more and see if the results are the same. Oh no, I am actually getting better speed, so that's a problem if the results are consistent over time. So that's some strange things here. I might have to do another test with the Cisco card also, to check if there are some differences. And now it's getting much better speed. And it says that the average access time is 67 milliseconds. Strange. I will actually run it once more and see what the result will be. Now it's even faster. This is the same, the read speed is the same consistently. I wonder if the write speed difference is because of some internal electronics and controller issues inside these devices. Strange. 14.5, so some of the results a bit faster, some a bit slower. I'm also going to run check disk again. Check it, I mean, sorry. Yeah, this is consistent. So the other test was not very consistent, but this was. And I'm now going to turn this off, and I'm going to check the results with the Cisco card. And now I don't need to go into the BIOS because the XT-IDE supports the auto detect feature. Yes. Yeah, let's see what's happening here. 1209, it's a bit slower. And now it was able to run these, and 0.5, 0.5, so it was the same as the other one. Last time it was not able to complete this, but as I said, this Cisco card is a very old device that I picked from, we can check once more here, see if the speeds are consistent. This card I picked from an old Cisco router. They was standing in the back of every kind of this equipment, so I do have two more of these cards. I was picking them out of a router on the recycling center some years ago. And then I have tested this, and I'm also going to test with this not so consistent test. Well, it's actually quite fast. I do seem to remember that 11 point something, 11.6 was the best. But of course this is a much smaller card, so yeah, and 14.3, that's actually quite good. And this is 70 nanoseconds, I think the milliseconds, I think this was 67 on the other one. So there clearly is a speed penalty on this, but I am going to remove these BIOSes, not these BIOSes, but the XT-IDE BIOS, and I'm going to very smart move. Yeah, like so. Then I have to start up, and I have to enter the setup screen to enter the parameters for the Cisco card into the setup. And it's this, it's the 492 and 16 and 492, even though it doesn't matter. Changes saved and boot. And now it's just the Quadtel BIOS and the 32-bit card. Fixed disk failure. Okay. I will go into the setup again. I did have a similar issue one time before here, because I did write something wrong here. It should be 592 and I wrote 595, so the same error I made last time, and no one was screaming at me. Yes, and we do the check it test first, like so. So just let's run check it and benchmark hard drive. Last time we was not able to complete this with this card, 1280 and 0.4. So this actually is faster, no doped with the Quadtel BIOS. And here we have to test several times now to see if this is consistent over time. 1183, 777. Yeah, we have to see. Run it at least one more time to be sure. 14-point IO flops. The fastest we got was 12 and 11 on the other card. 14 point. And I run the same test again, F3 repeat, and see what we get. Yeah, it consistently faster on the write speed every time we try, so there might be some internal caching or sorting thing that comes into play here. Yeah, the read speed is consistently the same. This was slower. Yeah, 14.6, so it was a bit slower. And one final test just to test my hypothesis about the write speed being faster each time. No, it's actually exactly the same. And this was a bit slower. That was consistent in the two tests before. Strange things. Yeah, but the latency here is 68 milliseconds, and on the XT-IDE it was 70. Yeah, so we have done some tests, and I can say that the results was a bit surprising. It is slower with the XT-IDE, even though it doesn't do 8-bit reads and writes. I could test this, of course, with an XT-IDE card, but I won't do that in this video. I don't have a working card as of right now, so I probably have to solder up some to be able to use a similarly performing system, because the one I have is one without an adapter for the cable, so we will have to mimic most of the setup in another way. It's, by the way, the same card, the card that I have as with a direct compact flash interface. It's from Surjay something, and it's the same card I do think that Tommy over at Arctic Retro has done some tests with XT-IDEs just recently. But that's enough for the bench here. We have some results, so I'm going to set this up in a table and compare them. Sometimes you get some unexpected results when you are doing these kinds of things, and I'm not totally surprised, but I am a bit surprised. I was thinking that the XT-IDE BIOS that has been in development for so long, and actually is based on previous codes, that it had made very fast and good regime on the interrupt 13 handling and so on, but it clearly is not. But this might be due to that the XT-IDE BIOS is made to be compatible with a lot of stuff, and it can be something with my implementation or configuration, but I don't think so, because this BIOS setup where I have this divided into even and odd EPROMs and 16-bit. It means that the reading and writing to every, the reading from every BIOS routine, it's much more efficient than if you do it 8 bits at a time and have to buffer it and present it to the CPU as an 16-bit. But the differences are not that great. And I've calculated some averages here. What I can say is that the averages, they varies a lot, because this diskette by James Pearce did have some inconsistent results with these compact flash cards. And even though we do have a consistency in this, that the Quadtel BIOS is faster than the XT-IDE Bios, the differences between the 32 megabyte and 128 megabyte card is about as big and bigger than what we had with the XT-IDE Bios. But the fastest result for the check-it transfer speed that we have here, both of them are larger than this one. So I made every measurements again, and I made 3 takes on every situation, the 32 and 128 megabyte card with the Quadtel BIOS and with the XT-IDE BIOS. So was this the best way to do this? Probably not. I should have used a third disk test tool, but since the results at the check-it and the transfer speed was consistent, and they confirmed the other results, I think we do have something that is not totally accurate, but not wildly inaccurate either. And what are the differences? They are not that big. You can see here the transfer speed. This is the speed from the check-it utility, and this is the dark blue one. So while this is the XT-IDE and this is the Quadtel BIOS, so you can see the slowest result on the Quadtel BIOS is a bit faster than the fastest result on the XT-IDE BIOS. So this one and this one you can compare, and this one and this one. So it's not a huge difference. And the same can be said here. This is the transfer speed. On the write issues, there you have the slowest writing speed is actually with the Quadtel 32 megabit card, but the other ones are almost identical. And the same can be said here about the random transfers and I/O operations. You compare this one with this one and this one with this one. So it's not a huge difference. And this is the average access times. And here you can see some differences, because this one, and it's 3 milliseconds difference. And the same here on this one, the 32-bit card. It's about 2 millisecond difference. So there are some differences, and the seek time is also faster with the Quadtel. So it does seem that the XT-IDE BIOS has an unoptimized code, and that can be because they have made the translations for allowing larger drives, where the Quadtel BIOS don't handle drives larger than 504 megabytes. The XT-IDE BIOS actually has to handle some translations of the drive parameters and the addressing as it goes in and out. So it probably has some good explanation. Is the Quadtel BIOS, is this actually faster than the XT-IDE BIOS? Yes, it is. It is faster, at least when you are keeping below 504 megabytes. And will I be testing this anymore? I don't know. Probably it could be wise to test also against an XT-IDE 8-bit card to see how that fared against this. I might do that, but it will not be in this video. Yes, and that is the end of this video. This has been a video with 2 topics. Everything has been about the 5170, of course, but I did test the speed of the EPROMs, did the measurements and did an explanation of that. And I also did the measurements against the drive speed for the 5170. I was thinking of making 2 videos about that, but it's better to make it in a slightly longer video, so those of you who are interested can watch both parts. Otherwise, it will drag out in time. And I've done some interesting things for me in this video. Interesting to know about the XT-IDE Bios and the differences. And measuring on the EPROMs actually gave me a surprise. The 130 nanosecond-ish delay that I have means that I can probably overclock this computer to, yeah, maybe as much as 12 megahertz something before I run into huge troubles. At least 10 or 11 megahertz should be okay without adding wait states on the read. So some interesting thing has been discovered. There is still a lot of mess behind me on the bench, and I'm not totally sure if I'm going to do one other project on the 5170 board, or if I'm going to jump into some C64 stuff. So I'm not totally decided on that, but please hit like and subscribe. Go back, watch some of my older videos, and I will really appreciate it if you do subscribe to the channel, and most of all, if you leave a comment below the video. I actually can, yeah, get some feedback of what I'm doing wrong and what I'm doing kind of terrible. So until next time, see you, take care.